Hello students, in this video we'll use the residue theorem to evaluate an integral that involves a ratio of exponential functions. Let's let a be in the interval 0, 1 and consider this family of integrals, integral from negative infinity to infinity of e to the ax over 1 plus e to the x dx. I want to integrate down and figure out a formula for these family of integrals over here. Okay, excellent. These are actually come up when we talk about like these integrals actually pop up a lot in number theory, which is interesting, right? So we're going to figure out how these things involve that relate to the gamma function pop up in number theory too, which is really cool. Okay, so how are we going to figure this out? So let's do the following. We're going to do our standard thing. We're going to introduce a complex value function which agrees with this function on the real axis, and then we're going to look at a contour that encapsulates at least one singularity of this function. Okay, so great. Let's do it. So let's consider f of z, which is e to the a z over 1 plus e to the z, right? And the following contour. And the contour so here r, little r is just a number that's greater than 0. Looks like this. It's going to be a rectangular contour. And then here's the imaginary axis. Here's the real. So the real axis is down over here. That's my real axis. My imaginary axis is over here. And this is a height of, that is a height of 2. That point over there is 2 pi I. This point right over here, that's going to be important, is going to be pi times I. Okay? And of course, what's this number here? That is the number r. This is the number negative r. And so this is going to be r plus 2 pi I. This is going to be negative r plus 2 pi I. So there's my rectangle over there, okay? My rectangle has 4 pieces. It has the bottom piece, it has the top piece, it has the right piece, and it has the left piece, okay? So what can I say? The bottom, if I do this, if I make the contour like this, there's my contour. Okay? So on my contour, if I integrate over the integral over the bottom plus the right plus the top plus the left of our function over here, e to the a z over 1 plus e to the z by the residue theorem. So here I'm going to use the residue theorem. There's only one singularity. It's a simple pole. It's the residue. It's 2 pi I times the residue of our function e to the a z over 1 plus e to the z. E to the z evaluated at the point z equals pi times I, right? Now, of course, this pole over here, this is a pole of this function. Pi I is a pole, and it's a simple pole, right? Now, how can I see that? Because when I plug in, when I do the derivative of 1 plus e to the z, the derivative of 1 plus e to the z is e to the z, and e to the pi I is equal to negative 1. So the derivative does not vanish at that point, which means it's a simple pole, right? So this is a simple pole. Okay, so this becomes 2 pi I, then the calculation is easy, it's just the numerator, so it's going to be e to the a z over what? It's going to be e to the a z over the derivative of this thing, which is just e to the z, evaluated at what? Evaluated at z equals pi I. And so what we're going to have over here is we're going to have a, what are we going to have? We're going to have a 2 pi I, an e to the I a pi, over what? Over e to the I pi is negative 1, so that's a negative 1. So this is going to be, I can write this actually as a 2 pi, and then e to the I a pi, all divided by, well, negative I is the same as 1 over I, so I'm going to put that 1 over I in the denominator. Okay, excellent. Because we're going to see sine in our answer, right? So I'm going to put the I in the denominator. Okay, so in other words, that integral over here is equal to 2 pi e to the I a pi over I. Great. Now I need to do all 4 of these calculations. So let's do what each of these things is. So this is going to be 4 things. The integral over b of e to the a z over 1 plus e to the z dz is equal to what? The integral over the bottom is just the integral from negative r to r, integral from negative r to r of e to the ax over 1 plus e to the x dx. So as r goes to infinity, this converges to what we want. Great. Okay. Let's next do the integral over the top. The integral over the top of e to the az over 1 plus e to the z dz is going to be what? On the top, we're going from what to what? My z is really what? On the top, z is equal to x plus 2 pi I, right? And where does x go from? X is going to go over here from r to negative r, right? X goes from r to negative r on the top. And I have an e to the I, e to the a x, and then plus e to the a 2 pi, so that's going to be e to the a 2 pi I. And then a what? Over 1 plus e to the x times e to the 2 pi I, but e to the 2 pi I is equal to 1 dx. So what this thing is this thing is negative e to the I a 2 pi, the integral from negative r to r. By putting a negative sign over there, I can flip the limits of integration, and then e to the ax over 1 plus e to the x dx. In other words, this implies that the integral over the top, so the bottom part plus the top part, integral over the top plus the bottom of our function f of z dz is really 1 minus e to the 2 pi I a times integral from negative r to r of e to the ax over 1 plus e to the x dx. Great. So the bottom and the top give me this factor. So as r goes to infinity, it gives me this factor times the integral I want. Great. Okay? Now what's next? Let's do the integral over the right and the left. So what's the integral over the right? F of z dz. Well, this is going to be what? I'm going to, on this part over here, z is equal to what? It's equal to r plus what? I can say r plus I t, where t goes between 0 and 2 pi. So this is going to be the integral from 0 to 2 pi of what? Of e to the a, and then now I have an r plus it over what? Over 1 plus e to the r plus it. And then what's my differential over here? My differential is going to be just I dt. So I dt. Okay? And now what's the only other difference over here? The only other difference is that on the left part, we're just going to go from negative, instead of positive r, we're going to have a negative r over here. Great. Okay? And then that's wonderful. Because what's going to happen as r goes to infinity over here? As r goes to infinity, let's think about what's happening over here. So note, as r goes to infinity, what's happening over here? Let's do the modulus of this thing. The modulus of this is less than or equal to now the modulus of this thing over here, like that. And the modulus of I is just going to be 1. So this is less than or equal to, this is going to be the integral from 0 to 2 pi. And then we'll have an e to the ar over 1. We can do e to the rt, of course. We can do by a triangle inequality. We can say it's going to be e to the rt, and of course, e to the it is 1, so minus 1 dt over here. Now, as r goes to infinity, what's happening to this thing over here? So a is less than 1. So this expression over here, if I multiply this expression by e to the negative ar, that's going to give me a positive exponential denominator. So this thing over here is going to tend to 0, right? And the same thing is true for, that proves that as little r goes to infinity, the integral over the right goes to 0, right? So there's no contribution from the right over here. And then similarly, by the same calculation, we have that the integral over L of f of z dz tends to 0 as r goes to infinity. Good. So in other words, what have we just shown? We've just shown now, we can put this all together, that this expression over here, so in other words, 1 minus e to the 2 pi ai times our integral that we want, let's call this integral over here, let's call this integral I for integral, times I is equal to this residue, so that's 2 pi e to the I a pi over I. So therefore I is going to be what? So our integral is going to be 2 pi e to the I a pi over I times 1 minus e to the 2 pi I a, like that. Good. And then what's going to happen over here? So now I can multiply by e to the negative ai, and what will that become? This is going to become 2 pi over and then what? And then I, and then e to the negative I a pi minus e to the I a pi like that. And I can put the numerator on top, so I can put this as a 2 over pi. I'll put the I on top, and then I'll have a what? I'll have an e to the I a pi minus e to the minus I a pi, right? And of course, that is just going to be pi over the sine. This is going to be pi over the sine of a pi, right? Because the sine of a pi is going to be e to the I a pi minus e to the minus I a pi over 2i, so that's just the reciprocal of that. So our integral over here is exactly equal to, our integral is going to be pi times the cosecant of what? The cosecant of a pi. So by using the residue theorem and using some basic properties of sine and cosine, we were able to compute this integral over here, and this integral will pop up again when we start discussing problems in number theory, right? So remarkably, this is related to the gamma function. So we're going to see that this integral over here is essential when we're going to figure out symmetries of the beta function and the gamma function along a certain diagonal in the complex plane. Thank you very much.